All right, quick overview for the 4 homework questions. Starting with number 30, this is the one with the wrecking ball. We've got the building being knocked down. You're standing underneath it, so right here. And the wrecking ball is going to be released from here. And you want to find the time it takes for the wrecking ball to get from its starting spot to the bottom before it hits you, so you can get out of the way. So what you have to know for this one is that the period is a time to go from one spot to the other side and back, so from amplitude to other amplitude and to return. So what we want to know is what portion of that do we have to worry about? And we only want the time to go from the amplitude here to the bottom, which is a quarter of that time. So 1/4, another quarter, that's halfway through, and then another quarter and back, right? So out of the whole trip there and back, we only want 1/4 of it. We're given the length of the pendulum. We know that t equals 2 pi root L over g is our pendulum formula. So all I'm doing here is finding out the period for the pendulum, 6.35 seconds, which again is the time from one amplitude to the other and to return. And then I divide it by 4, cut by a quarter to get my 1.59 seconds. Number 59, the 2-spring problem. We just got to be careful here with our consideration of what's going on with the forces. So at rest, I've got my mass right in the middle. Neither spring is stretched or compressed. This is the equilibrium position. And then it says I move it 1 centimeter to the side. So when I do that, I'm affecting both springs. So I have to think about what's going on with the springs. Right? This spring is stretched and wants to pull the block back to the left. Right? So the block wants to be at equilibrium. It's to the right side of it, so this spring is not happy being stretched and exerts a force to the left to try to restore the block, restoring force, to try to restore it to equilibrium. This spring on this side has been compressed by moving the block over, and it doesn't like that either. So this compressed spring wants to uncompress, which again would be to push the block to the left. So I've got one stretched that wants to unstretch to the left, and one compressed that wants to uncompress to the left. So both springs are working together to push the object, the block, to the left. So since they're both working together, we can add their forces together. So the total force is Kx, that's a spring force, 20 is K, given, and 0.01 is 1 centimeter, given. So 0.2 from the first, 0.2 from the second, 0.4 total. That's our answer to A. B says, what's the effective spring constant? Well, the effective spring constant would be the combined effect. They're working together, right? So I'm going to end up doubling their forces. K is proportional to force. I'm going to end up doubling their K. We can prove that because we have an effective force of 0.4 newtons from part A, trying to push this block back to equilibrium. The only stretch or compression was 1 centimeter, so 0.4 newtons for a stretch or compression of 0.01 meters, or 1 centimeter, would get me a K of 40 newtons per meter, which is double my original. And then finally it asks what the frequency is. So I'm going to find period first. I have all these T equals formulas, so that's my starting point. I know my mass. I have found my K. I'm going to use my effective K, both working together. So the time it takes to oscillate once, the period is 2 pi root m over k, 2.5 over 40 inside the square root. So 1.5 seconds is period. Frequency is just 1 over t, 1 over period. So 1 over 1.1 or 1 over 1.57 gets me 0.64 hertz for my frequency. Number 60 is the Bungee Man problem. So I've got Bungee Man the superhero who sees this bus that's moving at 21.2 meters per second, attaches a bungee cord to it, and then because of his stretching bungee cord, it goes 50 meters and then stops. So if this is my school bus, Bungee Man attaches the bungee cord when this thing's moving to the side at max speed. The bungee cord becomes anchored and the bungee cord stretches out 50 meters until this comes to a stop. That would be attaching the bungee cord when this thing's moving in the middle of the oscillation. So that's equilibrium, where it has max speed, then it slows down to the side. If I was allowed to oscillate, Then I'd pick up speed this way, go to the other side, stretch, come back to the middle, go back this way, stretch again. But essentially, I'm starting at the equilibrium and I'm going until the amplitude where I stop and turn around. That's a quarter of a complete oscillation, which I'm going to use later on. But what I have to do right now is just figure out what K is if it took 50 meters to essentially get rid of 21.2 meters per second of speed. So I used energy to do this. And honestly, my first attempt would have been to try to use period, because we use those way more often, right? You can see in part B, I ended up using this 2 pi root m over k formula. So my first thought was, can I use that? Because I've already identified that that time is going to be a quarter of the period. And the answer is no, because I don't know the timing and I don't know the spring constant, so I just don't have enough information to use this formula yet. So I've got to look somewhere else. And what clues me in or gives me a hint that energy is the answer to this is I'm comparing two different spots in the oscillation, right? The max speed equilibrium spot to the max position, no speed, amplitude spot. And my total energy should stay the same. I've got all kinetic in the middle, right? Technically, this is plus spring energy, but that's 0. And I've got all spring potential at the end, where again, technically my final kinetic is 0. So all kinetic going to all spring energy, same total. 1/2 mv squared in the middle, I have enough to find out my total energy. I know my mass, I know my speed. And then at the end, 1/2 kx squared, I know that I'm going 50 meters before I get to my amplitude and stop. The only thing I don't know is k. So I solve for k, 2,160 newtons per meter. Once I know k, then I can use my period formula to find out that t is 2 pi root 12,000 over 2160, so my period is 14.8 seconds. And again, I only have a quarter of the period here because I'm going from max speed equilibrium to stopping on one side. So just like in the first problem, I cut it by a quarter to find out the time for the relevant part, which is 3.7 seconds. Finally, number 61, shouldn't be too bad, just plug it in. You can see what I crossed out here. I mixed up my G values, but getting them in the right spot, 2 pi root L over G is going to be the formula for all three parts. At the equator, my acceleration is 9.78, so I just plug in 2 pi times the square root of the length, 1.000 divided by my G value. I get that each oscillation takes 2.009 seconds for the period. And then the textbook is asking me how long for 100 oscillations, so I just multiply the time from one oscillation by 100, and I get 200.9 seconds. Part B is going to the North Pole, and it gives me my acceleration value at the pole is 9.832. That is a higher G value, so I can stop and think here, should I get a higher or lower answer? G being in the denominator means I should get a lower answer, inverse proportion. And in fact, I do. I get 2.004 seconds for my time for one oscillation. Again, I want the time for 100, so I multiply by 100, and I get 200.4 seconds. Finally, I'm working backwards in part C. It tells me I go to a mountain, and I find that the time for 100 oscillations is 201 seconds, so divide it by 100 to start with. Each oscillation is 2.01 seconds. Plug that in. My length is still 1 meter. Solve for G, 9.77 meters per second squared. That's the lowest G value out of all three parts, and that makes sense because I have the greatest time out of all three parts. So again, that inverse proportion helps me sort this out.